Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
The next speaker is Garth Goodman, also of Carnegie Mellon University, and of course, when you're talking about data intensive, you're talking about storage, and considerable focus on the organization of storage subsystems. And every time I hear Garth talk about this, it makes me want to go back and...
Well, I'm not going to do that much on failure.
Okay. He's talked extensively about failure and failure rates, which always makes me feel like my data is in peril. And so Garth will tell us then about storage and data intensive compute.
So inside the project that you just heard about, we're interested in the differences in the computing software structures at scale. There really are two computing software structures at very large scale. There's internet services structures and there's HPC structures. And they're pretty much the only two large bodies operating at thousands of nodes and millions of, well, soon to be millions of cores. And I got a foot in both camps, and I sort of don't understand why they're two different camps. And that's the starting point of our notion is why should there be two different camps? Now, what I really love about all of this kind of stuff is the dominance of data. So I believe that computers should be built in order to process data, that the data causes you to say that you need a computer, the data causes you to create and design the parameters of the computer, and everything else in the compute side is completely subservient. And of course, that is not a very popular view amongst computer science. But it's where we're going. I love this story, but I've probably been told many times, but bringing a large amount of data and compute to a problem often enhances the ability of one science team versus a team that does not have that kind of ability. I believe this will effectively change the way everybody thinks about competing to do the best science, and that is they'll have to have the largest amount of useful data and the ability to do something with it. And I like the title, the unreasonable effectiveness of data. For me, this is really good because I've always cared about the data management system, and the data management system underneath these things is therefore going to have to be very big, very flexible, and very affordable. Some of the data sets that we've been locally identifying that are potentially huge, associated with science, not necessarily associated with any given discipline on how it should be computed. I don't want to go through them, but there's lots and lots of different scientists that want a huge amount of data for their science problems. I look at this and I say, well, how do I differentiate the HPC approach from the data-intensive scalable computing or the internet services approach? Mostly, when people stand up and say, look, there are things you can do with HPC you just can't do with data-intensive, what they're referring to is what I would think of as distributed shared memory. Some computation which is based on the total amount of things you can fit into memory, and that really does want to have communication cell to cell, so you need to have huge memory, low latency communication, and co-scheduling of everything. Right? What we've typically done in internet services is figured out how to do out-of-core operations where we flow over the data. We've broken it up into big pieces that we can afford to lose one and restart someplace else. So it turns into a relatively large amount of post-processing on a relatively small amount of captured data versus what we do in HPC. However, if you look at this community over here, there's more and more data analysis of the result of simulation. And that data analysis is more and more looking like the same kind of stuff that we would do initially from internet services based on transaction records. So convergence is very reasonable. So what I'm going to talk about specifically in this talk is a comparison between the storage subsystems in HPC versus data intensive and some of their differences. And my big theme is that many of these differences are artificial. They're based on the maturity of the code. Okay? My overriding goal is to get commonality so I can reuse software. Why do I want to reuse software? Well, because the big picture here is how does a scientist use 1 million cores effectively without having to put their career on the side and become a computer scientist for a long period of time. And there are many ways to do it, and I'm going to try not to have a database argument here. But mainly what I'm going to say is any programming methodology that gives you a relatively easy way of thinking of programming 1 million cores on a terabyte or a petabyte of data is a useful thing to explore at this point. The HPC file systems are much more mature. They have been doing this for 10 to 20 years at relatively large scales than the data intensive computing infrastructures. And they have always been dealing with semantics that are more demanding than we've currently got in internet services, particularly highly concurrent. And there is the possibility now of taking it, there is a danger even in HPC, it's highly proprietary, but there is a new emerging standard, the parallel NFS, which just got its RFC, 5661, that can stand up as being a standards-led solution to the HPC parallel file systems. And I would argue that would be a good choice as a substrate for the data-intensive computing as well. We want to reuse the data management tools. You get your petabyte, you bring up your open source tool to do replication in 3 different copies or 6 different copies. You feel good about the fundamentals of reliability, and then somebody says, what are you doing about backup? How do you deal with this data coming into the system? How do you deal with the data falling out of the system? What do you do about replication? And you start designing all sorts of back-end systems for the data management that you don't really want to do. You want to have that handled by the infrastructure that normally handles it. Okay, and the fundamental problem here is scale, fault domains, thousands of fault domains. Failures, the thing that Peter doesn't like is, and I'll tell a little story here, the projections going forward through exascale sizes is that the number of concurrent disk array reconstructions, the way they're currently being done, will go from maybe 5% of the time you're reconstructing a failed disk to there are 100 concurrent reconstructions going on, being rebuilt at every time throughout the lifetime of that system. We will probably not get there because we'll probably do things differently. But if we did them the way we are right now, it would scale to that. What that would mean is the performance analysis would always be done in the failure case. And you would never bother with the normal case because you're not going to experience it much. Right? That's going to change the way we do systems. So we will struggle hard to avoid doing that for a while. All right, so what we did is we took HDFS, which is the file system inside Hadoop, which is the open source implementation of MapReduce. And it is nicely layered. And we pulled out the file system, separated Hadoop from HDFS. We stuck in PVFS. PVFS is the parallel virtual file system. It is an open source HPC system. It's used extensively at Argonne in production. So it's a mature implementation. And I don't have a pointer, so I'm going to wander around a little bit. Sorry about that. You have a top button. Okay. So now this is really all in a Java layer when in Hadoop and HDFS. And so what we did was put in a little shim, and that little shim makes out calls to PVFS. Primarily what's in that shim is read ahead. And normally you don't do read ahead in a parallel file system because it leads to inconsistent data. But in the HDFS world, we do write once. We have no problems with inconsistency, so they have no problem reading ahead aggressively. We pass out file layout information that allows us to ship compute to the data by knowing where the data is. And we pass in replication because traditional HPC pushes replication down into the subsystem, tries to make reliability a property of the hardware and not a property of the software. And the data-intensive systems are making it a property of the higher level software. The result, in short, is when you pull it out of the box, this is HDFS, and you put in PVFS underneath, you go a lot slower. That's not the end of story. The read-ahead tuning, which isn't that hard, gets half of the difference gone away. And then if you expose the layout position, the other half went away. And this is typical. This one is a small system I think we ran locally, not a M45. But it's the same kind of architecture. So the short story here is that there is no performance difference when PVFS is on exactly the same hardware as HDFS for HDFS workloads. And that can be taken one of two ways. It can be taken that, gee, HDFS is doing pretty well against the mature PVFS system. And it can also be taken that it doesn't have any huge advantages over the more mature software at the same time. You can take it either way. One of the important differences here is PVFS has to be run on the same nodes to take advantage of the shipping compute to the data. And that's a really big shift to the way the HPC systems build compute versus storage. They would always put compute into nodes that are primarily doing compute and storage into separate nodes. Why? Well, because the storage nodes are going to be used for all the computations for all the storage everywhere, and you don't particularly want to be turning your supercomputer into a file server for someone's outside work. But that is fundamentally what we're doing with the more data-intensive approach. And it's not bad, it's just a big trade-off. The second thing is this way we do replication. Okay, looking a little closer, there are some interesting differences. The intellectual thing I want to get across here is, in a rewrite of the system for data-intensive, we take and throw traditional boundaries and APIs and toss them away and solve the problem differently. Here's an example of that. So in PVFS, as you change the number of clients that you are reading against a file, the file bandwidth grows linearly. There's more clients reading, more spindles are up and running, away you go. Everything is evenly loaded, you get every benefit. With HDFS, as you add more clients reading, you don't get more bandwidth linearly. Why? Because they're doing random assignment of the blocks to locations, and you don't get every spindle spun up all the time, and you get some congestion. So right off the bat, with a workload that is like a traditional file reading sequentially, you lose quite a bit in here. But this never costs HDFS any problem, because MapReduce doesn't tend to encourage you to process that way. MapReduce encourages you to break down your work into a big pile of queue of work and hand that queue over to the MapReduce job scheduler. And the MapReduce job scheduler load balances and keeps everybody busy. So it doesn't do the work at the time which causes the load imbalance, which causes this drop off. It picks something else farther down in the file and does that now because it'll keep the spindles all going. The net result is HDFS doesn't see any slower processing when you're going to read the whole data in whatever order the MapReduce job scheduler decides to run it in. So that boundary effectively says, yes, this is a bad layout from the point of view of traditional read access patterns, but if you know you're going to use the job load balancing and job control language that MapReduce gives you, you don't suffer from that, and there's a lot of benefits to random allocation because you don't have things in the wrong place when you lose something and you have to rebalance it later on. The big difference, of course, is that HDFS writes once and then doesn't write again. It doesn't support concurrent writing or even rewriting. So the result is that if you have to write something, then the completion time of writing a large file in HDFS, just one of them, is terrible because one node has to read the whole thing in and copy it to another location or generate all the data. One writer for one file. Whereas PVFS, of course, can do this in parallel, there's no problem. The net result of that is that HDFS trains its users to manage their data differently. The typical HDFS user thinks of a large file as a directory with a whole lot of pieces. And they pick up the directory and they move that around. Because now I can copy it with MapReduce firing off a job, copying each little piece, and I get the full bandwidth of the system. Right? It is a limitation of the underlying file system that they're changing with the behavior of their users. Right? It's currently not much of a problem, but if you do want that large file, and in HPC we see checkpoint users that generate checkpoints arguing strongly that they don't want to manage the 10,000 files or the 20,000 files. They want to manage just one. Hence, they do want the concurrent writing. So we did a comparison up on Yahoo M45, which is now part of the, and I just pulled this off. Did I? Yeah, I did. So, thank you. Oh, not yet. So we did a comparison of grep and sort, two of the classic benchmarks for HDFS and GFS before it. On the Yahoo M45, M45 is 500 nodes, 8-way, parallel. It's been available for research in disk-like computing to CMU for the past 2 years? Year and a half. And we did this by spinning off and a separate HDFS on it and a PVFS on top of it, just all run underneath their environment. And what I wanted to show is, for reading data, there's just no difference. For sort, which is, does a lot of writing, there's a big difference, and the big difference corresponds to the number of copies that are made and the network bottlenecks. So in M45, you have a relatively slow network compared to the amount of disk bandwidth that's inside. So the disk bandwidth locally is free compared to the network bandwidth. So HDFS, when it goes to write 3 copies, puts 1 locally and writes 2 remotely. The local one is effectively free, causing the significant difference in here. This is a complicated thing. That free one could create massive imbalance if you were writing a few large files, but of course the users have been taught to carry around a directory full of a lot of comparable size objects. So writing one locally, as long as you have lots and lots of MapReduces writing a lot of relatively small things, load balances that file as well. There's a lot of behavioral characteristics and mixed things that are going on here. Also, the network limitation is not fundamental. It isn't. You don't say it is a disk system because it is network limited. We're seeing in the cluster that we built, yes, we have one in here that is dual 1 gig E, but we also built one with 10 gig E, and our 10 gig E implementation can write remotely as fast as it writes locally. And you take away that bottleneck and that difference goes away. It's also the case that the Ether community, there's 2 papers I can point to now, have discovered fat trees in close networks. So as the HPC world has learned a long time ago, if you want to have high bisection bandwidth, you can build a 2-level routing network. Close tree is the classic one. The Ether world has figured out that they can do the same thing. And so the cost of providing higher bisection bandwidth is not necessarily anywhere near as much as you might think it would be. Okay, so PVFS, HDFS as underlying file systems. If I ignore the replication, they're largely, I can make them do almost the same thing. All right, now the replication. So HDFS does triplication. It does triplication GFS before it did triplication. This is, from my background as a RAID person from the 80s, a totally unacceptable overhead. That when you think and my students did this recently, they said, oh, we've got to move around a big pile of data. It's about 20% of the capacity of the storage. So that's 1/5 of each of the disks. That's not going to be too bad. But HDFS is going to triplicate everything. So it's 60% of the capacity of the entire storage. That turns out to be quite an issue. All right? So why is it that we're paying a triplication overhead? The main reason is simplicity. So when you do RAID over the nodes rather than RAID in a hardware subsystem, you're exposed to all the failure modes of all the components, not just the disk failure modes, all the computing failure modes as well, and that makes it messier. So I've dealt with this. We built a RAID over objects at Panasys, at the company I started, and you can do it. You can do it at giant scale, but it is quite a bit more complex than what GFS and HDFS actually did. What they actually did was they simply write 3 copies. And it's expensive. It makes lots of transfer. It uses a lot of space. But the repair and reconstruction operation, the guaranteeing your data is there, is moved off the critical path. All of the reconstruction is done in a background thread. So you write a lot of copies so you don't think you're going to ever be threatened. And then if a few of them go away, there's a background thread that runs around, discovers that you may not have full replication, picks those items, and makes more replicas. Right? And it's being done effectively more slowly than in a traditional RAID. A traditional RAID would work really hard as soon as a failure occurred to repair it, because they would be trying to operate with the smallest number of clean copies. And if they're operating with the smallest number of clean copies, then there's a fear that you will be in a high level of vulnerability if you don't clean up fast. What this code did was say, well, yeah, that's true. Let's make more copies so that we can tolerate that, and then we'll do it all in the background. All right. But that overhead, the space overhead, is still too much. So what we're going to try to do here is put a RAID algorithm into HDFS to give you back that space, and at the same time learn from the deferred asynchronous encoding and recovery. All right. So what we're going to do is we're going to write 3 copies, fire them out there right off the bat. Then the background job is going to run around, find places where there's 3 copies, and encode them down to RAID 5, 2 copies in RAID 5, or a RAID 6 implementation. So we'll still have the high protection. We'll still get the same amount of bandwidth, but we will delay the encoding operation and take it off the critical path for simplicity. There's a complexity here. I've got all these users that are trained to treat a large file as a directory of 10,000 little files. So it turns out that I don't have nice big files to compute RAID in. So I'm going to have to compute RAID across lots of files. And that's going to make a mess of my delete. But I'm not going to worry about that much here. So we have built this. The first one we built in a class project here last year was simply to replace one copy with RAID 5. So you wrote 3 copies. You go around. You find 3 copies. And you leave 2 of them in place. And you delete one and replace it with the XOR of a bunch of other nodes. We would go around and find a server that had the things that we want to compress already local. So we wouldn't use the network. That was a search process of finding a set of things that we can compress locally. And it doesn't change the performance of the system, as you would imagine, and saves the space, as you would imagine. We stopped because you can't extend that very well to higher levels of protection. The algorithm for searching for the right combination of blocks on an individual node that can protect against 2 failures is growing exponentially. So we didn't want to do that search anymore. And what we did instead was to change the allocation decision on when you first create the data, so it's pre-decided what you're going to group together. These are code words, and then we would go around and afterwards, when those code words are all filled in, compress them away. There are new interesting things. When we did RAID in the early 90s, we were deeply worried about the small write problem. The small write problem is when you change only one word in a stripe, then you have to update the parity. And you can either do that by reading everything in, computing, and writing out the new parity, or by noticing which bits you toggled in the data and toggling the corresponding bits. Well, we have that problem all over again in this scheme in deletion. So if we've XORed objects together that don't get deleted together, then to recover the space, I have to XOR them out of the freed up space out of the data sets. So we're looking at ways to use this freedom in asynchronous encoding to delay encoding so we can have triplication for applications that can benefit from it, and to delay deletion so that we can not do the XOR encoding. So this stuff, the codes, these are simple code. Actually, the difference in the codes is triplication, you write 3 copies of everything. RAID 5 plus mirroring, you have 2 copies and you do a parity, and the RAID 6 is a data and then 2 parity. After we did this, when we gave a talk in June at OpenCirrus, and the HDFS developers were in the room, and they told us in September they liked the idea and they built it. So HDFS has released this coding as a background compression of space for Apache HDFS. And, it's the fastest tech transfer I've ever done. The RAID 6 that we're currently working on is now implemented in HDFS, and here's an example. Widawat was in the room earlier. He ran this. We take 512 gigabytes of data. It gets triplicated up to 1,500 gigabytes when it gets created. And then this shows you the background compression job launching up and compressing away roughly 400 gigabytes in the RAID 5 plus mirroring, which HDFS is now doing, and 700 gigabytes of data in the RAID 6. And it goes at about, we can do about 4 gigabytes to 5 gigabytes a second in this system. So the compression can consume all of the bandwidth in the system, compressing the data away. It's not doing it remotely, it's doing it locally. So it's not stealing the network's bandwidth. The net effect of this is that we can get the space back while preserving the opportunity of having triplication for simplification and for multiple choices of reading. We get to decide when we do this. And so we can pick files that we want to leave triplicated because they're hotter and they would like more spindles for access, or because we think they're going to be reused again and we want that opportunity. All right, I think I'm about done, and I may be actually on time. So what we've done is we've started to look at exploring the differences in the software substrates and infrastructures for big data, really big data, for HPC and disk. And they're not as big as you might think. It's more a property of the maturity of the code. The write once by exactly one node is the kind of semantic that you would expect users to slowly but surely demand go away, and concurrent write will need to be supported. We see that already at Google, anecdotal comments about that kind of requirement from their users. Our directions. What we'd like to do is to integrate the best of both into our solutions. First of all, by allowing you choice in the substrates, but then also by maturing like taking RAID into HDFS is maturing it to a more HPC level quality. And then towards richer structure, a lot more metadata. We've got projects doing directories to millions, billions, and trillions of entries, directories that replicate the attributes so that they can operate like tables for storage management, and if they do it for the extended attributes, they could be tables for user applications as well. Okay, I'm done.
I'm hoping we'll have time for general discussion at the end of the 3 talks, but if there are questions regarding now, that'd be great.
I don't want to steal Alex's time. Nope. Thank you.